welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is lecture number 21, and this lecture deals with SPICE models and its equations. So, the outline of this lecture is we will discuss various models for MOSFETs in the context of the SPICE. We will also look into the limitations of the models which we have, and then discuss some other models which are different from SPICE models which we use. Now, traditionally this SPICE using very standard basic equations of MOS devices and even p-n junction diodes. So, the first level basically deals with that. So, the computational time is relatively small, but accuracy is also being compromised if you go for level 1. As you progress in level, the accuracy of the model increases, but so does the complexity of the model. Now, the first generation models which we have, and these the first generation models are primarily level 1, level 2 and level 3 models, which we will be actually going in details across this lecture series. Then we will look into the second generation model, which is basically your BSIM, which is a Berkeley simulated models. So, this is basically second generation models, and then we have a third generation model which gives me BSIM 3. So, BSIM 1 and BSIM 2 are primarily second generation. Up till level 28 SPICE model files gives me level second generation, and the third generation models are basically till level 48 and till BSIM 3 models. It goes even up to level 7 as well. Or the increase in the level has to do with more so to do with the various physical phenomena that you incorporate within the model. First generation is a basic model, second generation and third generation are superimposed on the first generation. For example, you can do a subthreshold modeling, you can do a stress modeling, you can do a noise modeling, gate leakage, temperature variation. Even now if you look at your SPICE model and HSPICE model of Synopsys, you can actually do, for example, heating effect, temperature variations, how does it influence the device characteristics. So, the whole domain of SPICE models have been divided into these 3 generations as such. Now, as I told you, the first generation is a fully analytical MOSFET model based on first principles. So, this is the first generation, and when I say based on first principles, I mean to say effectively that from the first principles of physics you can actually derive the model for a MOSFET and then try to formulate policy for doing the first generation model. I will give an example. So, let us take a level 1 model of first generation model. Typically they are used to simulate large digital circuits, and they also provide a higher level of accuracy for timing and gives you a very low simulation time. So, the convergence time for level 1 model, convergence time, right, is relatively very small for level 1 model, that they are quite small in level 1, right. And so, you can get the convergence and you can get the output result at a very fast pace when you do a level 1 model, but the cost you pay for it is of course accuracy, and typically you can do some digital circuits as well as some analog circuits here. Now, the level 2 models take into consideration the effect of bulk charge on current is being considered in this model. What does it mean is that if you remember your basic MOSFET theory, which we have already done in our earlier classes, the bulk of the transistor, for example, if you are doing an n-type semiconductor enhancement mode, the bulk is basically p-type. So, there is a depletion layer being formed, right. Now, the depletion layer charge which we define as, let us suppose we define that to be as QB, right, QB, if per unit area it will be QB prime, right, it is the bulk charge per unit area. This will actually define to me the total charge in the inversion layer, right. So, therefore, this is not taken into consideration in level 1, but however in level 2 this bulk charge effects are taken into consideration. Now, level 3 has got a much better accuracy as compared to level 2, but it is relatively converges faster as well. So, the advantage of level 3 model is that its accuracy is much higher as compared to level 2 and is almost equal to or more than level 2, but obviously its convergence is much better. So, both in terms of time taken to give you a result as well as accuracy is best for level 3, within the first generation analytical MOSFET models. Now, let us take up one basic sort of a equivalent circuit model for any MOSFET which you take into consideration, and then let us see how it works out. So, if you see here, we are actually looking into the intrinsic part. We are taking this as the intrinsic model, and we are assuming that this is my intrinsic part, and all the resistive and capacitive elements within the intrinsic part is at this stage may be constant, but at later stages may be bias dependent values will be attached to it. Let us go one by one as we start from drain towards the bulk, right. So, one thing is, if you look at this part here, this part, this is basically the current source which is happening, right, and this is between drain and source. So, this one is my current source, right. So, current source is basically equals to Gm times VGS. Gm is the transconductance multiplied by gate to source voltage will give you the drain current which is flowing through drain to source. Now, with that you have this, as I have not written it, this is basically RDS, drain to source resistance, right. The resistance of the channel itself is defined as RDS, and it will be obviously in parallel to drain current source. Now, if you remember very clearly, time and again we have discussed that for an ideal current source, the output impedance will be approximately equals to infinity, and therefore, if I have a resistance which is RSD here, right, source to drain, and you have a resistance which is infinitely large, the effective resistance therefore available to me is actually equals to RSD, because it is in parallel and the overall resistance will be always less than the least, and therefore, this network which you see in front of you will impose a resistance of approximately equals to RSD. Let us go one side and we see that between bulk and the drain you have this diode. Remember from where this diode is basically coming, this is coming from the fact that bulk to drain is reversed biased, and as a result there will be a reversed biased PN junction diode which will be placed between the drain and bulk. Why are we placing it? The reason we are placing it is to ensure that the depletion region is accounted for in the SPICE model file. Similarly, between bulk and source you will also have a depletion width. However, the depletion width in this case will be relatively lower as compared to that between drain and bulk, assuming that the drain potential is much on the higher side as compared to source, right. So, these 4 components, 2 drain component, 2 diode component, right, 2 diode component, and 1 resistor which is RSD, and 1 current source. This comprises of this bulk of the device itself. Once you have understood this basic concept here, we now leave the channel and go slightly towards the source and drain region. We will go step by step and see how it works out. So, you see this CBD which is basically bulk or body to drain is primarily because of this reversed bias diode, and typically this is a bias dependent capacitance, because as the drain voltage will go on increasing, the reverse bias increases, and as a result the depletion thickness increases and my CBD goes down. Similarly, if you look the CGD, it is gate to drain which you see. Gate to drain is coming because of the overlap of gate with the drain gate. So, if you remember during our earlier cases, if you have such an overlap taking place, this is my drain region, this is my source region, and if there is an overlap which you see here, this is my drain and this is the contact and this is your drain region, and this RD is basically the drain contact resistance which you get. Then since there is an overlap here and this is the metal gate here and this is the gate, then gate to drain is basically from this point to the oxide layer. And it is also, if you look very clearly, gate to drain is in a sense constant value, but its value depends upon how much amount of overlap is there of the drain end with that of the gate end. Similarly, if you look at CGB, which is the gate to bulk or gate to body, is primarily because from this point to this body point, where you have an oxide layer here and you will also have a depletion layer here. So, there will be a depletion layer here and there will be oxide layer here. Both will give you 2 capacitors in parallel, and what you will get, the overall capacitance which you will get for CGB is 1 by CGB will be 1 by C depletion plus 1 by Cox, which you will get, right. And this is where the value of your bulk charge becomes important, which determines the value of C depletion. So, we have been able to define CGB, CGD, CBD. Let us now come to CBS. It is basically bulk to source, right. It is bulk to source. So, there will be a depletion region here, because of which there will be a bulk to source potential at this particular point. So, there will be a diode attached here as well. So, this is my source and this is my bulk, and this CBS is available at this particular point. So, if I short source to bulk or source to body, then I will not get, I will get a value, but it will be independent of the bulk or source value. And what is CGS? It is gate to source. Which is gate to source is this, basically this one, which again depends upon the oxide thickness of the material. What is RG, RD, RB and RS? Are arbitrary resistance, which are basically contact resistances occurring at the gate, bulk, drain and the gate terminal. So, these are basically the arbitrary contact resistances which tend to take care of the total resistive value inside the system. So, when you do a circuit design using SPICE or otherwise, this is considered as an RC network. How does SPICE do is that the RC network is boiled down to effective value of R and C, and looking at that value, it is able to predict what will be the value of the tau for a particular given bias condition. Please understand that this current source which you are using, it can actually bias the device either in saturation or in linear region or in non-linear region. So, my consideration as of now is that we are using this I drain or drain current is effectively in the current source stage. So, it is actually in the current source. So, if you look very carefully, an interesting proposition comes here, is that when my MOS device is actually working as a current source, effective resistance is RSD, whereas if a MOS device is actually working as a resistor or a linear region, then it will be 1 by RSD plus 1 by R linear region, RL. So, this will come out to be RL RSD upon RSD plus RL, right. This will be the effective value of the resistance which is seen, and it will be a bias dependent again, because this resistance value will go on changing as you change the bias of the gate side. Now, if you divide this numerator and denominator by RL, then I get RSD divided by RSD by RL plus 1. So, as you can see here, as the value of RL starts to increase, which means you are going from linear region to the non-linear region somewhere here, then the resistance offered goes on increasing. Then it primarily means this quantity goes on increasing, which means this quantity goes on decreasing, which effectively means that this whole quantity goes on increasing, which means that the total resistance will actually be a bias dependent and will go on increasing as you move from the linear region into non-linear region into saturation region, where this is considered to be a current source. So, this is the basic sort of a 4 terminal small signal equivalence model of a device, right. Let us move forward now. Let us first talk about level 1 model. It is also known as Shikman-Hodges model, and it does not include subthreshold conduction. So, these are all post threshold such that VGS is much larger. VGS is much larger as compared to VTH, right. This has been done, and we also do not consider into any consideration that mobility is basically electric field dependent and there is a degradation in the mobility. No, mobility is actually held to be constant, right. And so, level 1 model does not take into consideration any subthreshold conduction, which is one of the conditions for leakage, neither it gives you anything about mobility degradation. Okay. It uses gradual channel approximation and also square law approximations. I will tell you what is this gradual channel approximation. We have already discussed in the class, I will just reiterate your memory in that sense. So, if you look at the gradual channel approximation, remember when your device lengths are very large, then I can go back and show to you. If the device dimensions are very large, this one, if you apply a drain voltage, the effective electric field is Vd by L on this side. So, if your L is very large, E will be relatively small. However, if your gate voltage has been applied and you are over threshold, then the electric field in the transverse direction, which is this side, is relatively very large, which is responsible for pulling all the charge carriers to a silicon dioxide interface, which means that the electric field along vertical direction, let us suppose EY, is much larger as compared to EX. This gives you the concept that I can actually use a one dimensional Poisson equation to solve and get the value of the variation of the potential along the y direction. But please keep in mind, what does gradual channel approximation actually helps you to do? Makes your mathematics simple, and you can use a single stage, maybe a first order derivative of the potential with respect to space, and you can still get a very good equation in one dimensions, right? And that makes your life relatively easy. Square law approximation is, if you remember, ID was proportional to VGS minus VTH whole square in saturation. So, IDS was proportional to VGS minus VTH whole square in saturation, and that is basically the square law which is hold. And the typical channel lengths where this GCA is applicable anywhere between 10 to 4 micron, or even less than that, even 2 micron, 2.5 micron channel lengths, you will be able to see actual IV characteristics and the simulated IV characteristics very close to each other. However, there is a problem here. The problem is that it is not able to predict the output impedance of the transistor in the saturation region. In the saturation region, if you look at the output impedance, it is relatively very large. However, this model, which is level 1 model, is not able to predict in a proper manner. So, let us look at some of the basic drain current equations for level 1 model, and this will make explain to you, and this is coming exactly from what we have discussed in our earlier cases. Now, you see, if you remember from our previous classes, ID was equals to half mu n Cox, right, W by L into VGS minus VTH whole square. This was in the saturation region, right, and you can see this is the saturation region I am talking about. Let us start from here itself, here itself. Now, you see it is exactly the same. However, we have an extra term here which has been added, which is 1 plus lambda VDS. And what is 1 plus lambda VDS? Lambda is basically known as channel length modulation parameter, channel length modulation parameter. If, let us suppose, lambda equals to 0, then this quantity will be vanishing, and what will be remaining is ID is independent of VDS, and therefore, if I plot, it will be something like this. At saturation, this is VGS say 1, then this is VDS, then you see that ID is almost independent of the value of VDS, it is almost constant, right. However, if there would have been a CLM, or a channel length model parameter, this is referred to as CLM, channel length modulation parameter, then the graph will shift something like this, that as VDS increases, then 1 plus lambda VDS increases, and you can see that the resistance is not a infinite value, but a finite value when you bias your device in the saturation region, right. So, this I have shown in this graph, and that is also explicitly shown here. Now, if you look carefully, there is a denominator term which is L minus 2 times LD. From where this is getting, I will explain to you now. Now, if you look at this figure here, then if you do not apply any bias anywhere, there will be a depletion region at this particular point. So, let me draw for you the whole thing once again. So, I am just drawing the part which will help me to explain properly. This is n plus, and if I do not apply any bias anywhere, I will get a fixed depletion here, because this is a p type substrate, I will get a fixed depletion here, correct. So, this will be gate, and this will be metal gate which we apply. This is the drain, and this is the source. This is LD, and this is also LD. Then the effective length is L minus 2 times LD. Why? Because this is the total dimension length, this is this minus this plus this. So, this is one LD, this is another LD. The effective channel length there between this point and this point is exactly equals to 2 minus LD, where LD is basically the depletion width on the source and drain side. You can actually look therefore in this case that my ID is proportional to 1 plus lambda VDS, and as a reason you will have such type of voltage variation taking place, not an absolute current source will behave. Let us come to the triode region. Triode region is exactly the same as the triode equation, which is this one, but we add to that 1 plus lambda VDS in the triode region, correct, and that also gives you a variation in the value of ID with respect to VDS. We define the threshold voltage as VT at 0 plus gamma times square root of 2 phi b minus VBS minus root of phi b. What is VBS? Is the body to source voltage, right? Now, if VBS equals to 0, you can automatically see that this quantity goes to 0, and therefore, this quantity, this one goes to 0, and therefore, VTH is equals to VTH 0. What is VTH 0? VTH 0 is the value of the threshold voltage when VSB equals to 0. You can understand this point, that when VSB or VBS equals to 0, then the value of VTH is equals to VTH 0, implying that whenever your bulk to source potential is 0 or they are shorted out, then the threshold voltage of the device happens to be equals to VTH 0, right. And then of course, you will have a cutoff when VGS is less than VTH, and therefore, your drain current will be equals to 0. So, there are 3 states of the device. One is of course, the cutoff region gives you a current of 0, and you also have a triode region and you have a saturation region. Triode region starts to behave like a resistive region, and the saturation region starts to also behave like a resistive region, provided you have a channel length modulation parameter effect available to it. The typical value of lambda in this case varies from 0.01 to approximately 0.09 or even 1 volt, 1.1.2. Higher the value, more slope this will become, and less resistance will it offer. So, this is the basic level 1 model which SPICE uses, and it is very simple and straightforward to get the result. Now, let us look at the effective channel length and channel width of the device. If you look at the first expression here, it is basically L scaled, which is the length of the device, multiplied by LMT, which is, this is also referred to as the length shrink factor, right, and WLMT, which is basically this one, is basically diffusion layer and the width shrink factor. So, what we have done is, I have multiplied my length or with a shrink factor, and we have multiplied the width with a shrinking factor, right. This way we can say that because of some lithographic problems, there is a shrinking factor coming, because of which the total length and width have been reduced by a certain value, because these LMT and WLMT are basically values which is between 0 and 1, more than 0 and less than 1. Now, if you look at LD scaled, it is basically the lateral diffusion to the channel from the source and drain region. So, this is basically if let me help you out to answer that. So, this is my LD which I was talking about, right. So, this is the value which I was talking about, LD scaled, and what we do here is that we have obviously WD scaled also available with us, and this value of DEL is basically my lambda or channel length modulation parameter, right. What does it tell me? I will tell you how I found out. Let me say an L effective we want to find out. L effective will be L scaled with the actual length multiplied by the shrinkage factor, which is LMT, and you will add X scaled minus 2 times LD scaled plus del scaled. Why? Because 2 times why? Because it is happening both source and drain end, right, and that has to be subtracted from the total channel length in order to achieve the effective length, and that is the reason you subtract 2 times LD scaled plus DEL scaled or DEL scaled. Similarly, if you look at the width of the device, then it has been scaled by a factor of W scaled, right, multiplied by WMLT, which is again defined as the sort of diffusion layer, and it includes diffusion layer and the width shrink factor. Now, XW or XD scaled, if you look, is basically my XW is basically my change in the value of W because of masking and etching away, and WD scaled is primarily lateral diffusion in the channel from the bulk along the width, right, from the bulk along the width. So, something is coming right from the bottom, which is basically having a much larger doping concentration, and it is trying to enforce itself to the top, because of which the surface is not flat and there will be a change in the effective value of your width. So, these two expressions which you see here gives me a brief idea about the effective channel length and effective width depending upon the various factors available to us. With this, let me stop here today, and what we have learned is that we have been able to formulate level 1, level 2 and level 3 model of SPICE, and subsequent to that we will be in a process of finding the value of CGS, CGD and so on and so forth. So, that we will take up in the next class. With this, let me thank you for your patient hearing, and we will meet next time. Till then, bye.